The transition to sub-2 nanometer semiconductor nodes requires a fundamental shift in lithography materials. High numerical aperture, extreme ultraviolet systems operate at power densities exceeding 10 watts per square centimeter. This thermal load drives protective pellicle temperatures up to 1,200 degrees Celsius. Traditional polysilicon and silicon nitride membranes fail catastrophically under these conditions. Polysilicon pellicles degrade rapidly above 400 watts of source power as temperatures exceed 600 degrees Celsius. This drops transmission below the 78% economic threshold. Silicon nitride extends thermal tolerance to 800 degrees Celsius but suffers from severe absorption. Carbon nanotube membranes present the only viable thermodynamic path forward. They maintain over 95% transmission, even at 1,000 watts of source power. Synthesizing carbon nanotube membranes to commercial standards presents severe material science challenges. The primary bottleneck is defect density. While defect rates fell from 1.50 defects per square centimeter in 2022 to 0.12 in 2024, they remain an order of magnitude above the commercial target of 0.01. Thickness uniformity across the exposure field is another critical constraint. Current chemical vapor deposition processes yield a thickness variation of 1.8 nanometers, missing the 1.0 nanometer target. This variation is driven by gas flow turbulence inside the synthesis reactors. Furthermore, metallic catalyst residues like iron or cobalt nanoparticles absorb extreme ultraviolet light. Removing these residues requires aggressive acid purification steps. However, these chemical treatments risk degrading the mechanical integrity of the nanotube network, reducing the membrane burst pressure. The transition in pellicle materials is structurally tied to the deployment of advanced lithography tools. Metal silicide pellicles served as a temporary bridge, peaking at 45% market share in 2024. However, as foundries transition to high numerical aperture scanners, carbon nanotubes will dominate the market. By 2028, carbon nanotube pellicles are projected to capture 60% of the market. This shift is accelerated by the rapid expansion of the global extreme ultraviolet scanner fleet. The installed base of these machines is scaling from 31 units in 2018 to an estimated 420 units by 2028. This compounding demand creates a highly concentrated supply chain vulnerability. Only a few specialized firms possess the chemical vapor deposition and purification capabilities required. Consequently, any delay in scaling carbon nanotube manufacturing will directly bottleneck global sub-2 nanometer silicon production. Trans-Alpine freight through the Brenner Pass reached 55.3 million tons in 2023. Despite European Union mandates to shift cargo to rail, road transport captured a record 75.6% of this volume. The existing mountain railway is physically limited by steep gradients of up to 2.6%. These steep inclines require costly double locomotive configurations and restrict train lengths to 450 meters. Consequently, rail volume has stagnated between 12.6 and 14.2 million tons annually. Meanwhile, road crossings surged to over 2,400,000 trucks in 2023. The long-term solution is the Brenner Base Tunnel, a 64-kilometer low-gradient flat rail link. However, excavation must traverse the Periadriatic Seam, a major tectonic fault zone. Highly fractured rock and high-pressure water inflows have delayed the projected completion date from 2025 to 2032. These geological anomalies drove an 86.6% cost escalation, raising estimates to €11.2 billion. As of mid-2024, workers have excavated 161 kilometers of the total 230-kilometer tunnel system. Until completion, the structural bottleneck in Central European logistics remains unresolved. In the absence of completed rail infrastructure, regional political friction has intensified. Austria has unilaterally increased block handling days from 26 in 2018 to 42 in 2024. This limits truck inflows to a maximum of 300 vehicles per hour during peak periods. This regulatory intervention has pushed peak traffic queues on the German border to 80 kilometers. The resulting delays cost freight operators over €150 million annually. This friction demonstrates how local environmental policies directly clash with international trade flows when physical infrastructure lags. Direct lithium extraction promises to bypass the 18-month lead times of traditional evaporation ponds. However, The process is bottlenecked by the thermal and chemical instability of proprietary active sorbents. At 80 degrees Celsius, aluminum-based sorbents suffer structural lattice collapse when exposed to high salinity brines. This degradation drives a nonlinear spike in operating costs. At 80 degrees, a 10.2% annual sorbent loss rate adds $580 per ton of lithium carbonate equivalent produced. At 100 degrees, this cost escalates to $1,050 per ton. This physical limitation is compounded by extreme supply chain concentration. Just 3 chemical conglomerates control over 85% of global high-purity adsorbent manufacturing capacity. This creates a single point of failure for global lithium diversification strategies. Second major bottleneck is subsurface fluid dynamics. A standard 20,000-ton plant must circulate 100 million cubic meters of brine annually. Returning this massive volume to deep reservoirs triggers severe mechanical and geological resistance. As depleted brine cools below 50 degrees Celsius, silica and other minerals precipitate. This scaling causes a cumulative well decline rate of 25% by year 5. Consequently, safe reinjection capacity drops to 65 million cubic meters. Operating above safe pressure limits of 15 megapascals is not a viable workaround. Doing so increases microseismic activity by over 300%. This risk of induced seismicity invites immediate regulatory shutdowns, mirroring the wastewater injection bottlenecks that plagued early shale gas operators. Direct extraction fundamentally alters the land and time economics of lithium production. It compresses processing times from 18 months to under 4 hours. It also reduces the required land footprint from 15 square kilometers to less than 0.5. However, these gains introduce severe resource trade-offs. Sorbent washing and elution require up to 180 cubic meters of fresh water per ton of lithium. This represents a 3.6 times increase over traditional evaporation ponds, threatening arid salar ecosystems. Furthermore, capital intensity is up to 108% higher than traditional methods. High-pressure reinjection wells and specialized extraction units drive capital costs up to $25,000 per ton of capacity. DLE does not eliminate bottlenecks. It merely shifts them from surface area to water and capital. The physical backbone of global cloud infrastructure relies on a highly consolidated mineral monopoly. Undersea fiber optic networks require optical repeaters encased in specialized pressure vessels. The primary material for these housings is beryllium-copper alloy. Upstream extraction is dominated by a single geological deposit in Utah. The United States controls 64.2% of global beryllium mining and 55% of downstream alloy production. This bottleneck mirrors the 19th century telegraph network, which depended entirely on gutta-percha latex from British Malaya. Kazakhstan holds 28.1% of refining capacity, but has zero domestic mining. China represents the only fully integrated competitor, controlling 25% of mining and 25% of alloy production. This triopoly creates an acute single point of failure for global telecommunications. Deep-sea repeater housings must withstand hydrostatic pressures of 8,000 pounds per square inch at depths of 5,500 meters. They must also dissipate heat from internal optical amplifiers directly into abyssal seawater. Only beryllium-copper alloy meets both structural and thermal requirements. Its yield strength of 1,150 megapascals allows for thin-walled pressure vessels. Its thermal conductivity of 105 watts per meter Kelvin is 15.6 times higher than titanium. Alternative materials like titanium or nickel alloys fail to dissipate heat, risking amplifier thermal runaway. However, beryllium-copper is highly toxic during dry machining and 12.5 times more expensive than structural steel. Consequently, fewer than 10 precision machine shops globally can fabricate these housings. This technical hurdle restricts the rapid scaling of deep-sea hardware. The surge in global cloud infrastructure is outrunning the physical supply of these critical housings. Annual subsea cable deployment is scaling from 61,000 kilometers in 2020 to 130,000 kilometers by 2026. This expansion drives a doubling of annual repeater demand to 2,166 units. However, specialized fabrication capacity is projected to reach only 1,720 units. The resulting 20.6% supply deficit has already inflated lead times. Delivery schedules for finished housings have stretched from 14 weeks to over 38 weeks. This material bottleneck directly delays the physical deployment of transoceanic data corridors. Hyperscalers can fund fiber optic production, but they cannot easily bypass the physical limits of beryllium metallurgy. The digital economy remains tethered to highly specific, intermediate physical realities. The global titanium dioxide industry is facing a structural feedstock crisis. Environmental regulations are forcing chemical plants to abandon the highly polluting sulfate process in favor of the cleaner chloride process. This transition has triggered a severe supply-demand imbalance for high-grade titanium minerals. Natural rutile reserves are depleting rapidly at major deposits in Sierra Leone and Australia. Supply is projected to contract by 47.5% by 2030. This depletion occurs as demand for chloride-grade feedstocks expands at a compound annual growth rate of 2.7%. The resulting structural deficit is modeled to reach 780,000 tons of titanium dioxide equivalent by 2030. This gap represents over 20% of total projected demand. The transition to cleaner pigment manufacturing is fundamentally bottlenecked by this geological limit. Bypass the depletion of natural rutile, the industry relies on upgrading low-grade ilmenite into synthetic rutile. This chemical upgrading process is highly energy-intensive. Operating rotary kilns above 1100 degrees Celsius requires 15.0 gigajoules of thermal energy per ton. When combined with subsequent pigment manufacturing, the cumulative energy footprint reaches 26.2 gigajoules per ton. This exceeds the energy intensity of the traditional sulfate process by 16.4%. The transition solves a waste crisis, but introduces a severe carbon penalty. The traditional sulfate process generates 2,500 kilograms of acidic iron sulfate waste per ton of pigment. In contrast, the chloride process using natural rutile produces just 250 kilograms. This massive waste reduction drives the feedstock shift despite the thermodynamic penalty of synthetic alternatives. The secondary supply chain for upgraded titanium feedstocks is highly consolidated. Western Australia controls 75% of global synthetic rutile capacity. This concentration exposes the global pigment industry to localized infrastructure and energy constraints within a single jurisdiction. Furthermore, 3 multinational corporations control over 85% of global high-grade refining capacity. This oligopoly exercises immense pricing power over downstream chemical manufacturers. The market lacks the diversity needed to absorb sudden operational shocks. Logistical vulnerabilities compound this concentration. Over 80% of global supply, totaling 2,800,000 tons, depends on just 3 deepwater shipping hubs. Any disruption at these ports will immediately halt the production of advanced pigments and titanium metal precursors worldwide. The global steel industry's transition toward low-carbon technologies requires high-grade, low-impurity iron ore. Unlocking these resources in Central Africa is fundamentally a maritime logistics challenge. The legacy port of Douala is restricted by a shallow 7.0-meter draft, capping vessel sizes at 20,000 deadweight tons. This limitation imposes a freight penalty of up to $15 per ton compared to deepwater shipping. The port of Kribai resolves this physical bottleneck. Its second-phase expansion provides a 16-meter draft, accommodating post-Panamax vessels and reducing maintenance dredging costs by 80%. The proposed mineral terminal targets a 24-meter draft. This depth will allow 300,000 deadweight ton Capesize carriers to load up to 100 million tons of bulk cargo annually. The resource base of the trinational Jaw rainforest region is world-class but entirely landlocked. Deposits like Belinga in Gabon offer premium grades of 64.0% iron. However, these assets require massive rail corridors to reach the coast. The Mbalem and Neba contiguous projects represent over 1.25 billion tons of combined reserves. Connecting these deposits to Kribai requires a dedicated 510-kilometer heavy-haul rail spur. Average iron grades across this regional cluster exceed 58%, far outperforming the global run-of-mine average of 48%. This high-purity profile is highly attractive for direct reduced iron steelmaking. Yet, the physical distance to the sea remains the primary barrier to commercialization. Developing this export corridor requires a highly synchronized, multi-billion-dollar capital stack. Total integrated capital expenditure is projected to peak between 2026 and 2028. During this window, annual capital deployment will exceed $5.8 billion. Rail infrastructure represents the largest single capital sink, consuming 45% of the total budget. This translates to $4.3 billion of the projected $10.1 billion total cost. The long-term economic viability of this corridor assumes a minimum 25-year concession period. It is highly sensitive to global iron ore prices remaining above $85 per dry metric ton. This capital intensity mirrors the development of Brazil's Carajás corridor in the 1980s, proving that Tier 1 mineral assets are ultimately macro-logistics challenges. The deployment of next-generation telecommunications and military radar is bottlenecked by radio frequency power amplifiers. Traditional silicon and gallium arsenide technologies fail at frequencies above 10 GHz. Gallium nitride on silicon carbide offers the necessary power density but faces severe interface defects. Threading dislocation density at the interface must be strictly controlled. Between 2018 and 2024, optimized chemical vapor deposition reduced these dislocations by an order of magnitude. This defect reduction drove 150 mm wafer yields from 45% to 86%. High-reliability military applications require defect densities below 1 × 10 to the 8th power per square centimeter. Exceeding this threshold causes localized electric field concentration. This leads to premature dielectric breakdown under high drain bias voltages exceeding 50 volts. The physical foundation of this technology relies on a highly consolidated substrate market. 3 global producers control nearly 80% of the supply of semi-insulating silicon carbide. This concentration leaves the defense and telecommunications sectors highly vulnerable to supply disruptions. Substrate lead times peaked at 32 weeks during the 2022 supply chain crisis. 150 mm lead times have stabilized to 18 weeks. The transition to larger wafers is stalled. 200 mm substrate lead times remain high at 30 weeks. This scaling bottleneck is governed by thermodynamics. Growing larger silicon carbide crystals requires managing extreme thermal gradients during physical vapor transport. High thermal stress induces structural defects in the ingot, limiting the commercial viability of larger wafer sizes. The internal architecture of a gallium nitride transistor reveals a critical thermodynamic trade-off. The silicon carbide substrate provides an exceptional thermal conductivity of 490 watts per meter Kelvin. This allows the device to dissipate intense heat from the active channel. However, the aluminum gallium nitride transition layers introduce a secondary bottleneck. These graded layers are required to mitigate the lattice mismatch and prevent wafer cracking. Yet, their thermal conductivity drops precipitously to just 30 watts per meter Kelvin, trapping heat near the junction. Despite this thermal barrier, the epitaxial stack is necessary to generate the active channel. Tensile strain in the barrier layer creates a high-density electron gas via piezoelectric polarization. This micro-scale materials science challenge dictates the ultimate power limits of modern radar and communication networks. The expansion of high-capacity transmission grids is bottlenecked by a single, highly specialized component. High-voltage bushings are critical for insulating energized conductors in grid-scale transformers. Currently, the physical supply of these components cannot match global capital allocation. Lead times for porcelain bushings operating above 500 kilovolts have reached 24 months. This represents a 182% increase since 2016. Even modern composite alternatives now require over 16.5 months to manufacture. This supply deficit has driven the global backlog to 4,250 units. The delay directly stalls the deployment of extra high-voltage substations. Without these specialized insulators, physical grid integration remains at a standstill. The production bottleneck is rooted in the thermodynamic limits of traditional materials. Wet process porcelain requires a 42-day thermal cycle in kilns heated to 1,250 degrees Celsius. This process consumes 28.4 gigajoules of energy per ton. Cooling these massive ceramic shells is highly volatile. Thermal stress causes microcracking, resulting in an average scrap rate of 18.5%. This structural fragility limits throughput and prevents rapid scaling of production. Resin-impregnated paper composites offer a faster alternative, curing in just 5 days. They achieve a tensile strength of 250 megapascals, far outperforming porcelain. However, this route replaces thermal bottlenecks with chemical dependencies on highly consolidated epoxy and silicone supply chains. This component shortage has systemic consequences for global decarbonization. High-voltage bushings now account for over 11.2% of total transformer capital expenditure. This is nearly triple their cost share from 2015, reflecting intense supply-side pricing power. Consequently, average commissioning delays for high-voltage transformers have surged to 22.5 months. This delay directly tracks the bushing supply curve. The physical reality of manufacturing has decoupled grid deployment from capital availability. Global ultra-high-voltage grid capital expenditure reached $32 billion in 2024. Yet, actual transmission capacity cannot expand without these critical connection points. The transition to renewable energy remains tethered to the physical limits of heavy industrial manufacturing.